Welcome to this introduction to linear regression. Linear regression belongs to a family of different regression modelling techniques. There are many different regression analysis techniques, such as logistic regression, generalised additive models, multi-level models, and many more. The simplest and most fundamental version of these techniques is linear regression, which is the focus of this video. The goal of regression modelling, quite broadly, is to understand the relationship between an outcome and a set of predictor variables. Linear regression can be used to answer two different kinds of questions. First, we might be interested in creating a model for prediction. For example, a real estate agent may want to build a model that predicts the value of a house based on various attributes we can measure, such as the size of the house, age of the house, whether it has a garden, and other factors. Here, the main goal of the model is to predict the value of new houses that the agent is going to sell. However, linear regression is also really useful when we don't care about prediction, but we want to estimate the relationship between a set of variables. For example, many psychology studies have explored the association between political beliefs, so whether your beliefs fall onto a spectrum of left to right, and other factors such as gender, age, and income. Linear regression can be used to understand relationships between different variables. In the past, the way statistics has often been taught is to memorise a large list of different statistical tests. For example, you may learn that when you have two continuous variables, you should use something like Pearson's correlation coefficient, whereas when you have data on multiple groups of individuals, you may want to use a test such as an ANOVA. However, all these different kinds of tests are just different versions of linear regression in practice. And there's a very nice blog post, which is linked at the bottom, which shows how you can implement these different statistical tests using linear regression. Therefore, if you gain a strong foundational understanding of linear regression, you'll be able to understand for free a whole bunch of other statistical tests. In linear regression, we have two different kinds of variables. Firstly, we have the variable that we want to predict, and this is sometimes called the outcome variable, the dependent variable, or the response variable. But these all refer to the same thing. We also have variables that we're going to use to predict our outcome variable, and these are sometimes called the predictor variables, the independent variables, or the explanatory variables. And again, these three terms are all used interchangeably. So when should you use linear regression? There's a lot more to say about this, and I'm only going to very briefly talk about when you should use linear regression. Firstly, linear regression can only be used when we have a single continuous outcome variable. So the key thing to note here is that we can't have more than one outcome variable. However, you can have 0, 1, 2, or 1,000 predictor variables in your model. On the internet, there are a large number of misconceptions that frequently arise about linear regression. One common misconception is that your predictor or outcome variables need to be normally distributed, and this is somewhat of an oversimplification. In fact, it is perfectly possible to have a binary variable or a categorical variable as your predictor. Another confusing misconception about linear regression is that it's limited to studying linear relationships between variables. In fact, with some very simple modifications, you can use linear regression to understand non-linear associations as well. And that'll be the focus of a future video. So in this video, we're going to start with a very basic example of linear regression analysis. So let's say we have an outcome variable that we'll call y, and a predictor variable that we'll call x. And let's say we want to understand the relationship between x and y. In this particular example, we have a dataset shown on the top right with 6 observations. The idea behind linear regression is that we want to create a model that can help us understand the relationship between x and y. The linear regression model, when we have a single predictor, looks like the following, and we'll break this down step by step. On the left of this formula, we have y, which is our outcome variable. Note that underneath this y, we have this letter I. What does this stand for? Well, y isn't any specific number, but y is a list of numbers. So on the bottom right, we can see that y is a list of 6 numbers going from 1, 5, 13, 4, 8, 9. I tells us which row in this data set we are referring to. So we could imagine that we have another column here, and it goes from 1, 2, 3, 4, 5, 6 to the very end. We can use I to refer to any of the elements in this list. For example, the value of y when I is equal to 2 is, in this example, 5. In other words, the second row in this data set has the value of 5 on the outcome variable. On the bottom right, you'll often see this added to the regression formula. All this is telling us is that I can only take on whole numbers, so it can go from 1, 2, 3, all the way to n, and n is simply the last number in this list. In this example, n would be 6, and this is sometimes referred to as the sample size. On the right of this formula, we have the part of the model that relates the predictor variables to the outcome, and we can split this into two main sections. This first section of the model is what we use to make predictions about the outcome. And this part of the model has two main components. Firstly, we have the regression coefficients, or sometimes called the beta coefficients. In this case, it'd be b0 and bx. This first regression coefficient is sometimes termed the intercept. And in this case, because we have x as our predictor variable, our next regression coefficient, or in this case will be called the beta coefficient for x. But if our predictor variable was age, for example, we'd simply call this the beta coefficient for age. Note that we don't have any i's underneath these two beta coefficients, and that's because in the formula, these are our constants. The goal of linear regression is to estimate the values of these intercepts and beta coefficients. So unlike y and x, which we know the values of in advance, we don't know the values of the intercept and the beta coefficient. And these are things that we want to estimate in our model. And typically we try and find estimates of the intercept and beta coefficient that provide us with good predictions about y. The final part of our regression model over here is the error. Inevitably, you'll find that in any regression model, we are never able to perfectly predict our outcome variable, and there's always going to be some sort of error. So one way we could write this model is that our outcome here on the left is equal to our regression model's prediction of the outcome plus some random error. So again, like the beta coefficient, this error term is not something that we know in advance. So as mentioned in the last slide, this part of our model is what we use to make predictions about the outcome y. The goal of regression analysis is to find good values of these beta coefficients, beta 0 and beta x, that help us understand the relationship between x and y. Let's say that we ran our regression model and we found that the value of the intercept was -1 and the value of the beta coefficient for x was 2. Our model would then look something like this. So here we're saying that the value of our outcome variable y is equal to -1 plus 2 times by our predictor variable plus some random error. How does our regression model make predictions about our outcome using our predictor variables? Well, the way this regression formula works when we have a single predictor variable is that we simply take the intercept and we add it to the beta coefficient for x multiplied by x. Let's see how this works for the first row of data. So if you remember, we can label each row of data using I, and I, when I is equal to 1, that's for the first row of data, and it goes all the way to 6, which is our sample size. For our first row of data, let's work out what our regression model would predict the outcome to be. So in this case, we would do -1 plus 2 times by xi. In this case, the value of x is 1. So -1 plus 2 times by 1 is 1. For the second row of data, our regression model would predict that the outcome is -1 plus 2 times by 2, which is -1 plus 4, which is 3. Let's run through again. So in order to predict the outcome y for this third row of data, we take the intercept, -1, and add it to the regression coefficient for x, which is 2, times by the value of x for this row of data, which is 6. So that is -1 plus 12, which is 11. We're able to do this for each remaining participant, or row of data rather. That's 5. -1 plus 8 is 7. This column of data that we've just worked out are our model predictions. These are the predicted values of our outcome given the predicted variables. However, we're not able to perfectly predict our outcome variable using this predictor variable x. For example, in our last row of data, so when I is equal to 6, the true outcome variable is 9, but our model has predicted a value of 7, which isn't 9, there's some error involved. And this is where our final part of the model comes into play, which is the error term. We can rewrite this formula so that our outcome is equal to our model prediction plus some error. Then another way of writing this is that our error term is equal to the outcome minus our prediction. And this is what we've just rewritten down here in this formula over here. So y is our outcome variable, and we've simply minused the value over here. So we have minus the intercept minus the beta coefficient for x times by x. To work out the error term for each row of data, we take our observed outcome and we minus it from our model's prediction. So in this first case, the outcome is 1 and our model prediction is 1. So 1 minus 1 is 0. And that makes sense because our models predicted the exact value of the outcome. There is no error for this particular unit. But for the next row of data, the observed outcome is 5, and our regression model has predicted a value of 3. So the error is 2. Now let's do the same for the rest of the data. So here we have 13 as the outcome, and our model's predicted 11. So we have 2. Now here we can see that our outcome is 4, but our model has predicted 5. And in this case, the error is -1. So here we can see that our error is negative when our model has predicted a value that's higher than the outcome. You'll see over here where the outcome's 8 and our model's predicted 9, which again is -1. And the last row we have 9 minus 7, which is 2. Let's go back to the scatter plot of the original data points. On the plot, we have each dot represents a row of data. This row of data here, where the outcome has a value of 13 and the value of x is 6, is represented by this data point over here. Let's mark on this scatter graph where our regression model has predicted the value of y. So for this first row of data, their outcome is 1, and their value in the predictor variable is also 1, and our model has also predicted a value of 1. So let's mark a little x here. For the second row of data, the outcome variable is 5, so it's probably this one here, and the x value is 2. So indeed, it is this data point over here. But our model has predicted a value of 3, so let's mark an x to where. I'll mark a little arrow to show where the data point belongs to the x. So this x is where the regression model, so it's the regression model's predicted value, sorry, I can't spell, prediction. So the x marks where our regression model has predicted where the value of y. For the next participant, their value in the outcome variable is 13, and their value in the x variable is 6, so it's this data point over here on the top right, but our model has actually predicted a value of 11. I'll just do this for the rest. So for this individual here, it is 4 and 3, but the model has predicted a value of 5. And then for this participant over here, the model has predicted a value of 9. And then for the last participant, we have the model has predicted a value of 7. So one thing that we should observe, if I've done this correctly, is that we should be able to draw a straight line through these x's where our regression model has predicted the outcome for each participant. One neat thing about this line that we've drawn is that our regression coefficients have a direct relationship with this line. Our regression model looked like this. So we have y is equal to the intercept plus the regression coefficient for x multiplied by x plus some error. And we previously said that our intercept value was -1 and our regression coefficient for x was 2. The beta coefficient for x tells us how much y increases on this line for every unit increase in x. So here, as we go from 0 to 1, so we go up 1 unit increase in x, our regression line, which represents our predicted value for the outcome, goes up by 2. If the value of this regression coefficient for x was 0, then we'd have a flat line. And if this regression coefficient was negative, the line would be slanting downwards in the opposite direction. This first beta coefficient, or intercept, tells us where this straight line intersects with the y-axis. So if we were to draw a y-axis here, when x is equal to 0, we will see that our regression line intersects it over here when y is equal to -1. A simpler way of thinking about this is that the intercept tells us the predicted value of y when our predictor variables are all equal to 0. And this is because when x is equal to 0, the value of y is simply equal to the intercept plus the error term. And that's because anything multiplied by 0 over here just becomes 0 and gets eliminated from the formula. So whilst it's intuitive to explain kind of regression using the language of prediction, we can also think about this part of the model over here as telling us the expected value of y when x is a given value. So when x is equal to 3, our regression model is telling us to expect a value of y that is around 5 in this case. And because of the error term, the observed values of y will kind of randomly be scattered around the expected value in the middle. So if the purpose of our study is not to predict the outcome, but to understand the relationship between x and y, rather than using the language of prediction and talking about how x is predicting y, we can instead talk about how the expected value of y changes with different values of x. So here we can see that the expected value of y increases when we have larger values of x. So over here, when x is equal to 5, the expected value of y changes to 9. And again, because there's the error term, the observed values that we'd find if we repeated this study and collected more data would be kind of randomly scattered around 9. So, to recap, this is our regression formula. On the left, we have our outcome variable, y. The betas here, or the b's, are the regression coefficients. Let's call them the regression coefficients. The regression coefficients are unknown and they're not in our data, so these are things that we have to estimate. The first regression coefficient is normally called the intercept, and that's because when x is equal to 0, our outcome, y, is simply equal to the intercept plus some random error. So the intercept tells us the expected value of our outcome variable when our predictor variables have a value of 0. The beta coefficient for x is sometimes called the slope, and that's because it tells us the slope in this line over here. So when this beta coefficient is positive, this line's going up. When the beta coefficient for x is negative, This line will be kind of going down like this. And when this beta coefficient is 0, it'll just have a flat line. The way I like to define it is that it tells us how the expected value of y changes for every unit increase in x. So in this case over here, as we go up 1 unit in x, we go up 2 units in y. And therefore, in this particular example, the slope for x was 2. The x in our formula, in this case, refers to our predictor variable. And it's possible to extend this regression formula to have more than one predictor variables. So if we have more than one predictor variables, our regression formula would look something like this. So y is equal to an intercept, that would keep the same. Again, we'd have our regression coefficient for the x variable. And let's say we want to include a new variable into our model, which we'll call age. Our new variable age will have its own beta coefficient, so let's call it the beta coefficient for age. And we'd simply multiply that by the variable age. And if you remember from before, these i's in our model simply are referring to the rows of data. Y, x, and age are both lists of numbers, which can be thought of as tables of data with different rows. So this first part of the model is what we use to make predictions about the outcome y. The last part of the model is the error term. So how do we find good estimates of these regression coefficients? Well, there are a lot of different approaches to estimating regression coefficients. The most common approach is called ordinary least squares. Ordinary least squares regression is one method of estimating the regression coefficients. The basic idea behind ordinary least squares regression, or OLS regression, is that we want to find the regression coefficients that minimize the error sums of squares, also sometimes known as the residual sums of squares. Well, what are these error sums of squares? Let's go back to our previous model. To work out the error sums of squares, we will begin by using the error terms that we calculated previously. To recap, the error is equal to the observed outcome variable minus our regression model's prediction of the outcome for that particular row. For example, in the second row of data, our observed outcome is 5, but our regression model has predicted a value of 3. So 5 minus 3 is equal to 2. The first step in calculating the error sums of squares is to square the error terms. To square any number, you simply multiply it by itself. So 0 multiplied by 0 gives you 0. 2 multiplied by 2 gives you 4. Minus 1 multiplied by minus 1 gives you 1. An important thing to remember is that if you multiply any negative number by itself, it will give you a positive number. All of these error squared values should give you positive numbers. Once you've calculated all the squared error terms, the final step is to simply add up everything in this column over here. So 4 plus 4 is 8, plus 1 is 9, plus one other 1 is 10, and the total over here is 14 if we add up everything in this column over here. And this gives us our error sums of squares, or residual sums of squares. And now we can see why they're called the error sums of squares, because we take the error terms, we square them, and we sum all of them up. Ordinary least squares finds these regression coefficients that give us model predictions that are as close as possible to the outcome. More specifically, the beta coefficients that it selects are those that minimize the error sums of squares and residual sums of squares. So when our model's predictions are closer to the outcome, we will have a smaller error term, and we'll therefore have a smaller error sums of squares in turn.